It is often not practical to determine a change in enthalpy experimentally. This is where Hess's law comes in. So it says that if a reaction is conducted in a series of steps, delta H for the overall reaction will equal the sum of the enthalpy changes for all the individual steps. So what does that mean? It means that we can take enthalpies of two or more known reactions to figure out the enthalpy of a third one. So let's see how that works with this visual representation here. So our target reaction is reaction 1. That's the one that we want to figure out delta H for. So it is one where we need to combine two yellow balls and a blue square to get this complex here on the right. And we are given these two other reactions and the respective enthalpies. So it turns out what we can do is we can add reaction 2 and 3. That's what I'm going to do here. So 2 plus 3. So I'm going to add all the reactants of 2 and 3 and add all the products of 2 and 3. So we have one yellow ball plus one blue square from reaction 2 plus this yellow ball blue square complex from reaction 3 plus another yellow ball from reaction 3. So those are the reactants. And then we look at the product side. Oops, let's make this the right color. And the product side of reaction 2, we have this fellow here, so yellow ball, blue square complex. And from reaction 3, we get yellow ball, blue square, yellow ball complex. Okay, and now we can tidy up a little bit. So because this fella appears on both sides of the equation, we can cancel it. And then we can add the two yellow balls together. So we have two yellow balls plus the blue square, so this thing. And that gives us the yellow ball, blue square, yellow ball, oops, wrong blue. Let's make it right. So yellow ball, blue square, yellow ball complex. And that is reaction 3. That is what we were after. So because we have added reactions, sorry, that is reaction 1, what am I saying? And because we have added reactions 2 and 3, we can also add the enthalpies of reactions 2 and 3. So delta H of reaction 1 will be the delta H of reaction 2 plus the delta H of reaction 3. So those are the individual steps that the definition is talking about. Okay? So reactions 2 and 3 are the individual steps for the reaction 1. So we're just going to add them together. So delta H for reaction 2 was 100 kilojoules. And delta H for reaction 3 was minus 65 kilojoules. And if we add them together, we'll get 35 kilojoules if my mathematics serves me right. So that is the delta H for reaction 1. So what have we done? We've added reactions 2 and 3. And so we have also added the enthalpy changes for reactions 2 and 3 to figure out the enthalpy change for reaction 1. Okay, this might have been a little bit abstract. So let's do something that's a bit more chemistry related. And I'm just going to have to move this out of the way. Put it over here. Let's bring this problem up. So here we have reaction 1. Nitrogen gas plus oxygen gas gives us nitrogen dioxide. And we have a delta H1 that we need to figure out. And then we are given two other reactions, reaction 2 and 3. In reaction 2, we have nitrogen gas and oxygen gas. That gives us nitrogen monoxide. and in reaction 3 we have nitrogen monoxide plus oxygen gas that gives us nitrogen dioxide gas. So once again, let's see what we can do. So firstly, let's identify the components. So in our reaction, nitrogen dioxide is a product, and we also have that as a product in reaction 3. In our reaction 1, nitrogen gas and oxygen gas are reactants, and we have those reactants in reaction 2 and reaction 3. So we can just add as is. So what we are going to do down here is we're going to add reaction 2 plus reaction 3. So firstly, all of the reactants. So we have nitrogen gas plus oxygen gas from reaction 2 plus nitrogen monoxide from reaction 3 plus another oxygen gas molecule from reaction 3 gives us 2 nitrogen monoxides from reaction 2 plus 2 nitrogen dioxides from reaction 3. And now we can tidy up a little bit. Nitrogen monoxide, or more precisely 2 nitrogen monoxides, appear on both sides, so they can cancel, which leaves us with nitrogen gas plus we have 2 oxygen molecules, so we're going to say 2 O2 gas, gives us the only product left, which is 2 NO2, 2 molecules of nitrogen dioxide gas. And that is our reaction 1. So what have we done? We have added reaction 2 to reaction 3. And so, in order to figure out delta H for reaction 1, we do the same with the enthalpy changes. So we're going to add delta H2 to delta H3. And that will be 180 kilojoules plus negative 112 kilojoules. And that should be 68 kilojoules. So delta H1 is 68 kilojoules. It is the sum of delta H2 and delta H3. Let's do another one, slightly different. So here we have graphite going to diamond, and we need to figure out the change in enthalpy for that reaction. And we are given the enthalpies for graphite going to carbon dioxide and diamond going to carbon dioxide. So, in our target reaction, diamond is a product. Here, diamond is a reactant. So we cannot use this reaction as is, but I'll come back to that. In our target reaction, graphite is a reactant. In our second reaction, graphite is a reactant as well, so we can use it as is. So let's look at reaction 3 again. Because diamond is a reactant in reaction 3, we need to flip it. So I'll do that. So we'll go CO2, so carbon dioxide gas, will give us C diamond plus O2 gas. So this is the reverse of reaction 3. So I'll call it R3. Because we've reversed it, we need to change the sign of the enthalpy changes. So the delta H for R3, so reverse of reaction 3, is now plus 396 kilojoules. Okay, and now we have our diamond as a product. So now we can add reaction 2 and reaction 3. And for clarity's sake, I will rewrite reaction 3 here. Sorry, reaction 2. So C graphite plus oxygen gas will give carbon dioxide gas. And the enthalpy change for that one remains unchanged because I have simply rewritten the reaction equation as is. So it's 394 kilojoules. And now we are going to add R3 plus 2. So firstly, all the reactants. So you have carbon dioxide gas from R3 plus C graphite plus oxygen gas gives us C diamond plus oxygen gas. Again, I'm looking at reaction 3 here. Sorry, reaction R3. And then finally plus CO2 from reaction 2. And once again, we can tidy up a little bit. We have carbon dioxide gas appearing on both sides, so we can cancel it. We also have oxygen gas appearing in equal measure on both sides, so we can cancel that as well. And we are left with carbon graphite, which gives us carbon in its diamond form. So what have we done to figure out delta H of 1? We have added reaction 2 to the reverse of reaction 3. So we're going to add those enthalpies as well. So delta H2 is minus 394 kilojoules plus, and the delta H of the reverse of 3 is plus 396 kilojoules, which means minus 394 plus 396 should be 2 kilojoules. So at the end we can say that the delta H for this particular reaction, so for a conversion of graphite to diamond, is 2 kilojoules.